Hello, my name is Ima Frank, your regular tutor. In this package, we are going to look at integration. Now, I would like you to bring your book and your Bible. As I'm teaching, you are going to write the note. It is not home video, so you don't just watch it. You don't just sit down and watch it, but you are learning. You are in lecture hall as of now, so bring your book, bring your Bible as I'm teaching you, and you'll be writing everything down. Now, before we start, let's look at the format of the teaching. The subject is mathematics, and then the topic is integration, behavioral objectives. At the end of this teaching, the students should be able to perform integration. The students should be able to perform integration of a polynomial function, integration of product function, integration of rational function. The students should be able to to perform integration by substitution. These are the objectives. Now let's look at the definition of integration. This is the revise or converse of differentiation. Integration is the revise or converse of differentiation. Now, in differentiation, we start from the function to the derivative, while in integration we start from derivative to the function. You see, and that is why we say it is a revise. In differentiation, we'll be given a function to find the derivatives, while in integration, we are given derivatives to find the function. Now, I'd like you to consider the function y is equal to x cubed. If I differentiate this function, we agree that dy dx will be equal to 6x squared. If you differentiate this function, you see, one thing about integration is that you must study differentiation before you can perform integration. So if you know you have not watched our lectures on differentiation, better you go back and watch differentiation so that you will know everything we are going to do in integration. So if I differentiate this function, I will have this. This is the derivative. I start with function to get the derivative. Now, to get back this function, I will integrate. So, I will integrate. And to integrate, I will say integral 6x squared. The x is because I'm integrating with respect to x. So I will say the x. And this will be the same as 6 integral x squared x. You see, this is a constant. So anytime we integrate, we bring out the constant and integrate the function. And if you have watched our lectures on differentiation, you see that when we are differentiating, we will minus 1, but when we are integrating, we will add 1. So that this will give us 6x 2 plus 1 all over 2 plus 1. And look at that. Which will give us 6x cubed all over 3. And 6 divided by 3 will give us 2x cubed. How is it? So we get back the function y is equal to 2x cubed. We get it back through differentiation. So that's why we say that differentiation, integration is the reverse of differentiation. You see, we integrate dy dx to get back to get y. We also integrate 6x squared to get 2x cubed, which was the original function, plus c. We plus c. We will talk about the constant c after now. Talk about the constant c. Why we should put c anytime we integrate. Alright. Let's look at why we should put c anytime we integrate. Now, look at the constants. The constant c. The constant c. Now consider these functions. Y is equal x cubed. That is number 1. Number 2. Y is equal x cubed plus 2. Number 3. Y is equal x cubed minus 5. We have 3 functions here. Now suppose we differentiate 1. We will have that the y all over the x is equal to 3x squared. Now let's differentiate 2. If you differentiate 2, we have dy all over the x is equal to 3x squared. You know, this is constant and this is constant, so when you differentiate, you get 0. Now number 3, dy all over the x will be equal to 3x squared, because this is also constant. Now suppose we want to integrate this function. Alright, let's integrate. We'll have integral dy all over the x will be integral 3x squared dx. Of course, I'm integrating with respect to x. So you see that we have integral dy is the same as 3 integral x squared dx. Integrating this, I have y. And this one will be 3x cubed, 2 plus 1, all over 2 plus 1. Okay? Then y will be 3x cubed all over 3. This can cancel this, so I have y is equal x cubed. Now, this y is equal x cubed that I'm having, you see that I have got back the original function, but I am only getting here. I can't get this. So we don't really know what is the value of the constants. And so what we do is to put plus c anytime we integrate, that there is a constant that exists and we don't know. But we can know the value of c if additional information is given about c. So we have the constant, the value of c. So that is how we put c anytime we integrate. Now we are looking at rules of integration. Number 1 rule is that integral of f plus g plus h dx will be equal to integral of f dx plus integral of g dx plus integral of h dx. Now, 2 that is I. Integral of k f of x dx will be equal to k integral of k f prime of x. F, it must be f prime of x because it is the derivative that will integrate to get the function. So k f of x dx, which is equal to k f of x plus c. Yes. And then we have another one, that integral 0 dx will be equal c if we integrate 0. So it's constant c. Now don't forget that next time, if we have integral f prime of x dx, this one is called integral sign. Integral sign. This integral sign. And this one is called integrand. Integrand. That is the function to be integrated. Is this. We are integrating this. So we call integrand. Why this sign? This sign is elongated s, meaning sum. We call it integral sign. So that is how we can use these rules to perform our integration. Now, we will look at integration of a function of linear function. Function of linear function of x. Now, let's take an example. Evaluate integral 2x minus 7 raised to the power 3 dx. So, if we have this, we do the solution in this way. Integral 2x minus 7 raised to the power 3 dx. We will let u is equal to 2x minus 7. Let u become this place. You see, this is like function of a function in differentiation. We'll let u become here. Now, the u all over the x will be 2. Yes, if you differentiate here, you have 2. So that will imply that the x will be 2, the u all over 2. To make the x object of the formula here. So it means that we now have integral of u raised to the power 3 du all over 2. That is what we have. Because this place is now u raising to the power 3 and the x is du all over 2. So if we do that, we can bring out the constant of integration, which is 1 all over 2. Then we have integral of u cubed du. With this, we can integrate here. You see how here b as x. Suppose here were to be x raised to the power 3. We will plus 1 and also plus 1 down. So that's how we will have 1 all over 2 u raised to the power 4 all over 4. And this will give us u raised to the power 4 all over 8 plus c. But u is equal to x minus 7. So that means integral 2x minus 7 raised to the power 3 dx will be equal to u, which is 2x all over 7 raised to the power 4 over 8 plus c. That's how it works. Plus c. So that is how we integrate a function of linear function, making this place u. And then you find the x. The x here in this context is the u all over 2. Then you bring out the constant of integration and then you integrate. So simple. So we are looking at integration of rational function. Okay, rational functions. Now, a rational function of the form mx all over n x, a function that is expressed in this form. So we call it rational function. The method used in evaluating the integral rational function includes, the methods include number 1, integral of f prime of x all over f of x dx. You see, this one is, you see a rational function of this form where the numerator is the derivative of the denominator. So when you are given a rational function, the first thing is to look, is the numerator the derivative of the denominator? If yes, we have a pattern. Another one is substitution of trigonometric function. We can also substitute a trigonometric function. We have another one, number 3. That one is a method of partial fraction. You can use partial fraction to solve a rational function, to integrate a rational function. Number 4, method of completing the square. Completing the square that we know in quadratic equation. So if you watch our lectures on quadratic equation, you see completing the square. Very, very clear how we put it. So these are the ways that we can look at rational function, and then we know how we apply. So let's pick examples. The solution 1, integral cos x all over 1 plus sin x dx. So what we'll do is we'll let u is equal 1 plus sin x. Let u be this. Okay, so du all over dx will be cos x. Of course, if we differentiate sin x, we know that we have cos x. So that the x will be cos x du. If I make the x of the formula, you see that the du will be cos x, yes, the u will be cos x dx, the u will be cos x dx. So what I have here now becomes integral u all over du all over u. Look at that. Because the whole of cos x dx is represented by the u, and 1 plus sin x is becoming u. So this thing now becomes integral 1 all over u du. So if we integrate 1 all over u, we now have ln u plus c. Log reading. You know, when you differentiate log u, you have 1 all over u. So now that we are integrating 1 all over u, we have ln u. Alright. But the u is equal 1 plus sine x. So what we do is to get ln 1 plus sine x plus c. That becomes the integration. So when you are given rational function, you look at it first, whether it is the derivative of the other. Now let's pick 2. Look at this 2. 2 is integral 4x minus 8 all over x squared minus 4x plus 2 dx. Now is the upside, that is numerator, derivative of the denominator. Of course, if you differentiate this, you have 2x. And if you differentiate here, you have minus 4. So it's not, but we can make it to be the derivative of this by saying that this will be equal to 2 integral of 2x minus 4 all over x squared minus 4x plus 2 dx. You see, if we do that now, then this one becomes the derivative of this. Because if I differentiate this, I'll have 2x. If I differentiate this, I'll have minus 4. So if that happens, I'll now let z is equal x squared minus 4x plus 2. You see, I'm using z here. I can use u, I can use z, I can use whatever I want to let it become. And so if that happens, it means that the z all over x is equal to 2x minus 4, so that the z will be equal to x minus 4 dx. Now this function becomes integral 2 dz all over z. And if I integrate it, this is 1 all over z, dz. So we have 2 ln z plus c. But we know that z is equal x squared minus 4x plus 2. So that will give us 2 ln x squared minus 4x plus 2, yes, plus c. So this becomes the results of the integration. So that is how it is done. It's very simple to do. We are looking at method of substitution using trigonometric functions. Example: integral dx all over x squared plus a squared will be equal to 1 all over a tan inverse of x all over a plus c. If you integrate this, it will give you this. Take note of this. But we can show. Now look at the rule. We have integral dx all over x squared plus a squared. Now I'm going to let x is equal a tan theta. See, I will let x is equal a tan theta. Call this equation 1. Then the x all over the theta will be equal to a sec squared theta. That is what we know, that if you differentiate tan theta, you have sec squared theta, which implies that the x will be equal to a sec squared theta d theta. That is, if you make the x subject of the formula here, you have this. Now if that happens, it means that integral dx all over x squared plus a squared will be the same as integral, you see the x now is a sec squared theta d theta all over x squared. You know, x is a tan theta. So now that we have x squared, we have a squared tan squared, yes, tan squared theta plus a squared, because a squared is this. Now x is this one. X is a tan theta. Now we have x squared. So a squared tan squared theta. Right. And we can now see that this thing can be written as a sec squared theta d theta all over, is it here? I will factor out a squared. So a squared bracket tan squared theta plus 1. I can write it that way. And if I write it that way, tan squared theta plus 1 is the same as sec squared theta. So this will give me integral of a sec squared theta d theta all over a squared sec squared theta, because I put sec squared theta, because tan squared theta plus 1 is sec squared theta. That means this, the whole of this can cancel the whole of this, remaining only a, because we have a squared here. So I have integral 1 all over a the theta. That is what remains, because a cancel a here, remain 1a. So this cancels all of this, so remain b. And this is a constant, so it can give me 1 all over a integral the theta. And if I integrate theta, I will have 1 all over a theta plus c. Now let's go back and find the value of theta from 1, because from 1 we see that x is equal a tan theta. So it means that tan theta is equal x all over a from here, and that only theta, it implies that only theta will be tan inverse of x all over a. That is the value of theta. Theta is tan inverse x all over a. So if you bring that and fix it here in the place of theta, so you will have that will be equal to 1 all over a tan inverse of x all over a plus c. Okay, so that gives us this proof we are able to show. Now let's take example. If you have integral of the x all over x squared plus 16. Now look at that. They give you this to integrate. So you can see that this one is the same thing as this. Meaning that we can write this thing as integral of x all over x squared plus 4 squared. I see. And without wasting time, if you let x is equal 4 tan theta and then follow this process, you will arrive here. Now look at x is equal 4 tan theta. Then the x all over the theta will be 4 sec squared theta, which means that the x is the same as 4 sec squared theta the theta. And now we have integral of the x. The x is now 4 sec squared theta the theta all over 4 square, 4 square, which will give us 16. 4 square there is 16. And then we have tan square theta plus 16. So if you have that, you can write this as 4 sec square theta the theta all over 16 bracket tan square theta plus 1. And if we do that, we will now have You see, this can cancel here. This can cancel here. So if it cancels, we'll have, and this one will also, this is sec squared. So let me put it first. 4, we have integral for sec square theta d theta all over 16 sec square theta. So that the whole of this will cancel the whole of this, and we'll have 1 all over 4 integral 1 all over 4 the theta, which will give us 1 all over 4 integral the theta, which is equal to 1 all over 4 theta plus c. But theta is equal to tan inverse, which we have seen. So we have that this will be 1 all over 4 tan inverse of x all over 4 plus c. That becomes the integration. So the short way is, if they give you this, just conclude here. So by this we are trying to show how it works. So that's how it works. Another example is when we have integral the x all over square root of a squared minus s squared. Look at this, square root. So it will be equal to sine inverse of x all over a plus c So let's see how we have it that way. Now, integral the x all over square root of a squared minus x squared. Let x is equal to a sine theta. Call that 1. Now, the x all over the theta will be equal to a cos theta, which implies that the x will be equal a cos theta d theta. So that integral the x all over square root of a squared minus x squared will be equal to integral a cos theta d theta. The x is taking a cos theta d theta all over square root of a squared minus a squared sine squared theta. A squared sine squared theta. Because x is a sine theta. Now that we have x squared, so you have a squared sine squared theta. Now this can give us a cos theta d theta all over square root of a squared 1 minus bracket 1 minus. I'm just factoring out a squared, so 5 times here I'll get back this 1 minus sine squared theta. And we know that this will be integral a cos theta d theta all over square root of a squared, then we have cos squared theta. You know why? Because 1 minus sine squared theta will give us cos squared theta. So this will be the same as integral of a cos theta d theta all over a cos theta. Because if you square root here, you have a. Square root here, you have cos. Now here, a cos theta can cancel a cos theta. So what we have here is integral the theta only, of which when we integrate theta, we now have, when we integrate the theta, we now have theta plus c. We have theta plus c. Now, but theta from here, theta will be equal to sine inverse of x all over e, so that we put plus c. Therefore, integral of the x all over square root of a squared minus x squared will be equal to sine inverse of x all over a plus c. So that is how it is. That is how it is. Now, I'm going to pick example. Example. Integral x all over square root of 9 minus x squared. We can write this as integral x all over 3 squared minus x squared. You know, 3 squared is 9. So, without wasting time, we can conclude that this will be the same as sine inverse of x all over 3 plus c. So that is how it works. Alright, now another example is when we have integral x all over square root of x squared plus a squared. You see, this one will be equal to sine inverse of x all over a plus c. You can also show, you know, integral of the x all over square root of x squared plus a squared, or even though we say a squared plus x squared, it still be the same. Now I will let x is equal a sine theta, so that the x all over theta will give me a cos theta, which implies that the x is equal to a cos theta the theta. Now, what it means is that we now have integral a cos theta the theta all over square root of a squared and then cos square theta plus a squared. You know, because we have that x is sine square theta. Sorry, this place will be sine square theta. Sine square theta. Because that's what we say. X is a sine square theta. Now that we have x squared, we have a squared sine square theta plus a. And we can write this as integral of a cos theta the theta all over square root of a square. Then we have sine square theta plus 1. Of course, this will give us integral a cos theta the theta all over square root of a square. Then this place will give us cos square theta, because sine square theta plus 1 is cos square theta. And if we square that, we have integral a cos theta the theta all over a cos theta. Because square root of a square will give us 8. Square root of cos square theta will give us cos theta. So the whole of this can cancel this. And then we have integral of theta. If you integrate this, you have theta plus c. But theta from here can give us theta is theta from 1. From this equation 1, put it equation 1. Theta from 1 is equal to sine inverse of x all over a. Therefore, now the integral of x all over square root of x squared plus a squared will be equal to sine inverse of x all over a plus c. So that is how it works. So that, for example, if I have integral of x all over x squared plus 4, then I will quickly conclude that this is the same as integral of x squared plus 2 squared. And immediately you have, square root sign here. And immediately you have something like this. It is the same as sine inverse of x all over 2 plus c. You know, this a is taking the place of 2 now. So you just have the answer in that way, following this substitution. So that's how it is done by substitution. We also look at the partial fraction, method of partial fraction. So this one is method of partial fraction. Example, evaluate this function. You know, this method is used to evaluate rational function where the numerator and the denominator are polynomials. So, suppose you want to integrate this, you will first of all resolve it into partial fraction. Of course, we know how we can resolve it to partial fraction if you watch our lectures on partial fraction. Alright. Now, I can write this as first thing I will do, let me look for the denominator first and know how the denominator look like. I will let f of x is equal x cubed minus 2x squared minus 5x plus 6. So now let me assume 1 first to see whether 1 is a zero of these polynomials. Then I will put 1 minus 2 1 squared minus 5 1 plus 6. So that this will give me 1 minus 2 minus 5 plus 6. 1 plus 6 is 7. 7 minus 7 is 0. Alright. So 1 is the zero of the downside, meaning that x minus 1 is the factor. So I can use the factor. Now I want to find other factors. If you watch our package on partial fraction, you really understand what we are doing there. So that I now divide this x minus 1 divided by x cubed minus 2x squared minus 5x plus 6. So this divided by this will give me x squared. This times this will give me x cubed. This times this will give me minus x squared minus 5x. And then this will give me minus x squared. If I minus is minus 2x minus minus. So making here plus. You see how mathematics relates. From partial fraction, you can use it to integrate. So a better watch our lectures on partial fraction is well simplified so that you understand these facts. Okay. Now, I'm going to divide this again. So now minus x. Minus x times x will give me minus x squared. Minus x times minus 1 will give me plus x. So we have plus 6. Now minus 5 minus x will give me minus 6x. Okay, so we now have minus 6. Minus 6 times this will give me minus 6x. Minus 6x times 1 will give me plus 6. So if I subtract, everything is 0. So I now have x minus 1 as a factor. I also have x squared minus x minus 6. This is quadratic. Now, in this quadratic, we know that this quadratic, two numbers that will give us minus 1, and when we multiply, give us minus 6, are minus 3 and plus 2. Minus 3 plus 2. So, we now have x minus 3 and x plus 2. So, these are the factors in the denominator. So we can now see that integral 2x squared minus 4x plus 3 all over x cubed minus 2x squared minus 5x plus 6 dx is equal to integral of 2x squared minus 4x plus 3 all over x minus 3 x minus 1 and then x plus 2 dx. You see, we have broken down the denominator to have it this way, so that we can take the partial fraction relatively. Alright, so if we have this, we can now find the partial fraction of this, which we know that it will be 2x squared minus 4x plus 3 all over x minus 3, x minus 1, then we have x plus 2. You see, we have kept integral sign. We keep integral sign first. We deal with the partial fraction. And then in this side, we will assume a x minus 3 plus b x minus 1 plus c x plus 2. You know, these are linear functions and different. When the denominator is different, it's different linear function. So in our lecture on partial fraction, you can get it all. Okay, so it means that 2x squared, you see, I'm supposed to take LCM of this. So even if I take LCM of this, I will have that A will times this and this, B will times this and this, and C will times this one and this one, all over this again, so that the two will cancel. I think our lectures will help you on that. We really deal with it one after the other. But this one, we are just trying to borrow partial fraction to solve this problem. So we may not explain it in details, but you can just watch the lectures, you get it all. So this is the same as a bracket x minus 1 x plus 2 plus b bracket x minus 3 x plus 2 plus c bracket x minus 3 and x minus 1. Now I'm going to put x is equal 1. I'm putting x is equal 1 so that this place will be 0. If I put x here is equal 1, the whole of this will be 0. The whole of this will be 0. So I can now get the value of b. So if I do that, I will have 2 of 1 squared minus 4, 1 plus 3 will be equal to b, you know, we'll put 1 here. So 1 minus 3 give me minus 2. And I put 1 again here, will give me 3. So minus 3 times minus 2 will give me minus 6. So I have minus 6b. I'm putting 1 here, I'm putting 1 here. Times if you have minus 6b. Then this one is 2 minus 4 and 3. So this plus this will give me 6. No, 5. This plus this is 5. 5 minus 1 will give me 1. So everything here is 1. 1 is equal minus 6b. So that b is minus 1 all over 6. That is b. Minus 1 all over 6. I've got b. So I'm going to also put x is equal 3. If I put x is equal 3 here, then 3 minus 3 will make b 0. And this side will also be 0. So we'll get the value of a. Now, put x is equal to 3, we have 2, 3 squared minus 4, 3 plus 3 will be equal to a bracket 3 minus 1 and then 3 plus 2. So 3 plus 2 is 5. And then 3 minus 1 is 2. 5 times 2 is 10. So what I will have here is 10a. Then coming to this way, this is 9. 9 times 2, 18. And this is 12. But 18 plus 3, look at this, 18 plus 3, it was 21. And this is 12, as minus 4 times. So we have 21 and 12. It's 11. 11 minus 2 will give us 9. Okay, so everything this side is 9. And then we have 9 is equal to 10a. So that a is equal 9 all over 10. That is a. Then, after that, I also need c. And for me to get c, I have to put x is equal minus 2. So if I put minus 2 here, it will make it 0. Minus 2 here will make it 0. So put x is equal minus 2. So we have 2 minus 2 squared minus 4 minus 2 plus 3 will be equal to you see everything here and here will be 0 if I put minus 2. So if you make only that, so we have c minus 2 minus 3, and then I also have minus 2 minus 1. So what do you observe here? It's 4. Minus 2 squared is 4. 4 times 2 give me 8. So here is also plus 8 plus 3. So you have 19. 19 is equal, this is a minus 3, this is minus 5. So that is 4 times you have 15. 15c. So that c is equal to 19 all over 15. That is the value of c. So we have got a, b, c. Now, what it means is that in this place that we assume these values, we can now see that it will be the same as a. A is 9 over 10. So we have 9 all over 10 integral of the x all over x minus 3 plus another one. You know this a is here. So by the time I put 9 over 10 in the place of a, then I will have this. Then we have another one, which is b. B is minus 1 all over 6 integral of x all over x minus 1. Then we also have plus 19 all over 15 integral of the x all over x plus 2. Okay, so that will be the same as 9 all over 10 leave x all minus 3. Yes, if you integrate this, the x, if you remove this, the x, you have 1 all over. So if you integrate, you have ln of that minus 1 all over 6 ln of x minus 1 plus 19 all over 15. We also have ln x plus 2. Okay. Right. Now, what we have here is that this is positive, and we know how logarithmic function works. So I can bring that here, so that we will apply addition law. Yes, addition law in log. So we now have 9 all over 10 ln x minus 3 plus 19 all over 15 ln x plus 2 minus 1 all over 6 ln x minus 1. Now, since this is plus, we will have ln, we have x minus 3. In plus we multiply. When it is plus in logarithm we times. So I will now take this one up, which is 9 all over 10 times x plus 2. We also have 19 all over 15 divided because of this minus, divided by x minus 1 raised to 1 all over 6 plus c. So that becomes the results of the integration. At least I know if you are not too familiar with partial fraction, or most of the times you don't know logarithmic function, how it operates, it will be difficult to understand. But what you do is you have a playback of it, follow it gradually, you understand it. Integration of trigonometric function. Now, the first one, we have integral of sine x dx. So if you integrate sine x dx, you will have minus cos x plus c. Now, the second one, we have integral of cos x dx. If you integrate cos x with respect to x, you have sine x plus c. Now we have another one, which is integral of sine square x dx. Now if we express this in double cosine of double angle, we will have that integral of sine square x dx, in double angle, 2, cos 2x, we express this in double angle, cos 2x is equal to 1 minus 2 sine square x. Look at that. So if I take this back related to this side, I will have that 2 sine square x is equal to 1 minus cos 2x. So that sine square x will be equal to 1 all over 2, 1 minus cos 2x. So I can now integrate this. Integral of sine square x dx will be equal to 1 all over 2, 1 minus integral 1 minus cos 2x plus 2x, okay? So now if I integrate this, I will have, that with respect to x, I mean with respect to x, I will have x minus, see, if I integrate cos x, I will have sine x minus sine 2x all over 2. Don't forget that we still have half here plus c. Now this time this will give us x all over 2 minus sine 2x all over 4 plus c. So anytime we integrate sine square x, we will have in this form x all over 2 minus sine 2x all over 4 plus c. Alright. Now we want to take the third one, cos square x, integral of, as the fourth one, you have cos square x dx. It will be equal to the same thing. If we express it, cos 2x will be equal to 2 cos square x minus 1. And then we also see that if I take minus 1 to this side, so I will have that cos, I will have that 1 plus, or plus 1, or 1 as this coming here, to have plus 1 plus cos 2x will be equal to 2 cos square x. Now, only cos square x will be equal to 1 plus cos 2x That is, we divide it by 2, we have 1 all over 2. 1 over 2, 1 plus cos 2x. So I can now integrate cos square x, where I will have 1 all over 2 integral 1 dx plus integral of cos 2x dx. So what it means here is that I will have x plus, of course, if I integrate this, I will have sine sine 2x all over 2 plus c. Now remember that we have half that follows it. So times it will have x all over 2 plus sine 2x all over 4 plus c. So when we so the next one, we are going to look at integral of sine cube x dx. Now we can write this as integral of sine x times or sine square x times sine x dx. Now if I tie this in this, I will have the same thing. You will see that this is the same thing as writing integral of 1 minus cos square x. Of course, you know that from trigonometry, sine square x is the same as 1 minus cos square x. The ability to integrate trigonometric function is knowing the identity. We know the identity. You can use that. So, and then we have sine x dx. So if I times it, I will have integral of sine x dx minus integral of cos square x sine x dx. So if I integrate this, I will have minus cos x, and then if I integrate this, I will have plus cos. Remember that this is cos square x. So if I integrate this, I will have cos cube all over 3 plus c. Yes, if I integrate cos square times sine x, cos square x times sine square x, I will have cos cube x all over 3. So this is how we can express this one. So we have solved these ones. I'm taking this one now. That is integral of sine 3x sine cube x dx all over cos square x. We want to integrate something like this. We can also express it using identity. You know, this thing will be the same as integral of sine x times sine square x dx, but the whole of this expresses this of the sine cube x all over cos square x. Now this is the same thing as writing integral of sine x bracket 1 minus cos square x. Yes, that is using identity. Okay, the x all over cos square x. Now if we use this times here, we will have sine sine x, this and this, minus cos square x sine x all over cos. If this thing is like this, let me, because the whole of here divide here, so it's cos square x, cos square x, cos square x. And then when we look at this, we can now see that here this one can cancel this one. So what we have here is sin x all over cos square x minus sin x. Remember, we are integrating it with respect to x. So what we will have, this one is then analyzing 1 all over cos x times sin x all over cos x. Because this times this will give this, and this times will give this, minus sin x. Now this is sec x. 1 all over cos x is sec x, which we know, and sin x all over cos x is tan x minus sin x. So integrating it with respect to x, we have integral sec x tan x dx minus integral sin x dx. So we know that if we differentiate sec x, we have sec x tan x. So now that we are integrating it, we have sec x. Now if we integrate this, we have minus cos. So that minus times it, we have plus cos x plus c. So that is how we can evaluate such integral. You see how important identity in trigonometry is when we want to express this. So we take the last one, which is integral of sin x cos square x dx. So in this way, anytime we want to integrate something like this, we look at this power. Look at this power. This is odd number 3, and this is even number 2. Now, this even number, we will let u is equal to cos x. Let u is equal to this one that carries even number, cos x. And you see that the u all over the x will be equal to minus sin x. Of course, if you differentiate cos x, you have minus sin x, which means that the x is the same as minus du all over sin x. Alright, that is the x. But we can look at this function, this xt, we can write it as sin square x sin x, yes, and then this is u. Now u squared, because we said that u is equal to cos x, so you have u squared. Then the x is given as du all over sin x, which means this sin x can cancel this sin x. And now what we have here is integral of sin square x u squared minus du. Now we can still express this as as 1 minus cos square x, because sin square x is the same as 1 minus cos square x. And then we put u squared minus du. But we still look at it that cos is here, which is equal to u. So we now have it in this one, integral of 1 minus u squared, and then we have u squared here again minus du. Now I'm going to use this to open. We times it. Everything here will use it and times it. So if I times it, I will have minus u squared du within here to times it. Then I will use it to times it. I will have plus u raised to the power 4 du, because this minus here implies this minus become plus. Now, if that happens, what I now have is integral of minus u squared du plus integral of u raised to the power 4 du. That means I will bring out my constant of integration, which is minus 1 here. So I have integral of u squared du plus integral of u raised to the power 4 du. Okay. Now this is a standard integral now. Can now integrate. So I will have u raised to the power 3 all over 3. That is 2 plus 1 plus u raised to the power 5 all over 5. That is 4 plus 1. Then that side is also be 4 plus 1. Now plus c. But u is equal to cos x. That was what we assigned u to be. So we will now substitute it here. So we will have minus cos cube x all over 3 plus cos 5x all over 5 plus c. Or you can write it in this way, that cos 5x all over 5 minus cos 3x all over 3 plus c. So that is how we can evaluate this type of integral. The next subtopic is integration by parts. Now, integration by parts is the reverse of differentiation. Differentiation of products function. Recall that if y is equal to uv, that dy all over the x is equal to u times dv all over the x plus v times du all over the x. That was what we did in differentiation to differentiate a product function, this product rule. Now, integrating both sides, we will have integral of dy all over the x, dx, because we are integrating with respect to x, will be equal to integral of u dv all over the x, dx plus integral of v times du all over the x with respect to x. And we see that this can cancel this cancel this cancel this. So what we will have is integral dy will be equal to integral u dv plus integral v du. Now, if I integrate here, I will have y. If I integrate this side, I have y. Now this side becomes integral u dv plus integral v du. But y is equal uv. Look at it. Y is equal uv. So I can put uv in this place. Then I have integral u dv plus integral v du. So that if I bring this one now, if I transfer this one to this side, I will have integral u dv will be equal to uv minus integral v du. Now this one is called integration by parts formula. Integration by parts formula. Okay. Now we are going to use it and apply in some examples that we are going to take. Now let's pick this examples. I integral x raised to the power 4 exponential x dx. I integral exponential minus 3x sine x dx. So we are going to deal with this. Now, solution of I. Integral x raised to the power 4 exponential x dx will let u is equal x raised to the power 4. Let u become this one. And this one, we call it the v. The v is equal exponential x. What we need again is du, so that du all over the x will be 4x cubed. If we differentiate here. And that if so, it means that du will be equal, look at this, cross multiplying this, will be equal to 4x cubed dx. Now, what about v? V is equal to integral of the v. That is the same thing as integral of exponential x, which is what? Exponential x. If you integrate exponential x, you have exponential x. So, we are able now to get u, the v, u, v, and the u in the formula. So, we can just substitute and start the integration. So, using the formula, integral u dv will be equal to uv minus integral v du. So we have uv, and u is what? X raised to the power 4 exponential x minus integral v is exponential x du. See du. Du is 4x dx. So that is how we put it. And when you do that, you have x raised to the power 4 exponential x minus 4. I'm taking out the constant of integration. So I have integral x cubed exponential x dx. So I have again x raised to the power 4 exponential x minus 4. Then I will start. See, here now, I will start again and make this one u. I'm starting here again to call it u. So call it uv. Of course, I will have x cubed exponential x, because if this is u and this is the v, if I integrate the v, I will still have exponential x. So uv minus integral v will be exponential x du. Now see the problem. Du in this aspect will become 3x squared dx, because this is u. Now, so differentiating this one now, I will have 3x squared dx. That is where the thing might confuse most students. Knowing that we are starting another u here, so this place will give you 3x squared dx. Now, x raised to the power 4 exponential x minus 4, x cubed exponential x minus 3 into, I'm bringing out the constant. So I have x squared exponential x dx. Now look at that. So this is the same as x raised to the power 4 exponential x minus 4. Then I have x cubed exponential x minus 3. You see, I'm going to start again. So my u here now become x squared. So uv will become x squared exponential x uv minus integral v du. V is exponential x. Now the u here is 2x dx, because if you differentiate here, you have 2x dx. Okay, so that is how it works. Now we go again. X raised to the power 4 exponential x minus 4. Then we have x cubed exponential x minus 3, x squared exponential x minus 2. You see, 2 is coming out. So if you bring out the 2, we have integral of x exponential x dx. Look at that. So you can see how we integrate and reduce to reach here. So we are still going. We want to integrate this again. We have x raised to the power 4 exponential x minus 4 x cubed exponential x minus 3. We have x squared exponential x minus 2. Okay, u again become x uv will be x exponential x minus integral of v is what? Exponential x du here will become dx, because if you differentiate this we have 1, so du become dx. Alright, so we have x raised to the power 4 exponential x minus 4. Then we have x cubed exponential x minus 3 x squared exponential x minus 2 x exponential x minus, you integrate this, and if you integrate here you have exponential x. Alright, so we can now start to multiply them out. We'll start from the inner one. So this will give us x raised to the power 4 exponential x minus 4. Then we have x cubed exponential x minus 3. Then we have x squared exponential x minus 2 x exponential x. That is, I'm using these two to times it. You have x exponential x plus 2 exponential x. Then I will go again. X raised to the power 4 exponential x minus 4 x cubed exponential x minus 3. Then I will use the 3 to open this bracket to have minus 3x squared, yes, minus 3x squared exponential x. Then I have plus 6x exponential x minus 6 exponential x. Then you remain this one to open. So we have x raised to the power 4 exponential x minus 4x cubed exponential x plus 12x squared exponential x minus 24x exponential x plus 24 exponential x. See, we are able to do that. And we now have x raised to the power 4 minus 4x cubed plus 12x squared minus 24x plus 24. You see, what I'm doing here is to bring out exponential x, because I have exponential x in common in all terms. So I just factor out exponential x plus c. So this becomes the integration of this function. We integrate here, this one will give you that. So that is integration by parts. We also pick this one because we have to show what that one involves. So let's pick example 2.
We are asked to evaluate integral exponential minus 3x sine x dx. So we'll let u equal exponential minus 3x. Then dv is sine x. Then du over the x is minus 3 exponential minus 3x. V is integral of the v, which is integral sine x. And that gives you minus cos x. Right. So from here, du will be equal minus 3 exponential 3x dx. Therefore, integral exponential minus 3x sine x dx will be equal uv. You know, we said integral. Okay, let's recall the formula that integral u dv is equal uv minus integral v du. So it means that integral exponential minus 3x sine x dx will be equal u, and u is exponential minus 3x v. V is minus cos x, and then we have minus integral v is minus cos x du is minus 3 exponential minus 3x dx. Look at that. So that is how it works. Now we can also continue here that minus exponential minus 3x cos x, then this one is plus 3. When you bring this one out, you have plus 3 integral exponential minus 3x cos x dx. So we see that this bond resemble here, except that there is sine and here is cos. So we have to go again next time. Minus exponential minus 3x cos x plus 3. Then we start the integration here again. U is exponential minus 3x. Now if you integrate cos x, you have sine x minus integral sine x, that is v, du is minus 3 exponential minus 3x, then dx. So, and this will give us minus exponential minus 3x cos x plus 3, then exponential minus 3x sine x plus 3 as there, plus 3 integral, yes, plus 3. Okay, this place is minus 3. This place is minus 3 because there is minus minus here, which is plus. Then here make it minus. So we have here minus. Then here is plus. Then we have exponential minus 3x sine x dx. Look at that. Now notice that here we have got where we started again. So what I will do is to let I equal integral exponential minus 3x sine x dx. So if I do that, I will have something of this nature, that I will be equal minus exponential minus 3x cos x minus 3 exponential minus 3x sine x plus 3 plus 3i plus 3i, yes, plus 3i, which is the same as saying minus exponential minus 3x cos x minus 3 exponential minus 3x sine x minus 9i. Okay, so I equal this. If I transfer here to this side, I'll have I plus 9i will be equal minus exponential minus 3x cos x minus 3 exponential minus 3x sine x. So 10i is equal this minus 3x cos x minus 3 exponential minus 3x sine x, right? So I become exponential minus 3x cos x minus 3 exponential minus 3x sine x over 10 plus c. So this is how that one can be integrated. It's a very simple matter. Okay, the next topic is reduction formula. Now we'll start with different reduction formulas. There are so many reduction formulas based on the function to be integrated, but I'm going to take few of them because of time. Now we'll look at integral xn. Integral xn, okay, exponential x dx. Let me start there. When I have a polynomial function and exponential function, what is the reduction formula for it? I know that integral from integration by parts, I know that integral u dv equal uv minus integral v du. So here, let u equal xn. Notice that. So the v is exponential x, which also means that v is exponential x, because if you integrate exponential x, you still have exponential x. Okay, so that means if I substitute this in this formula, I will have that integral xn exponential x dx will be equal, look at this, xn in the place of u, then exponential x minus integral v is exponential x, then du is nx n minus 1 dx. That could be written as xn exponential x minus, I have to bring n out, minus n, then integral x n minus 1 exponential x dx. So you see that what we have here is the same thing with here, only that this one is n and this is n minus 1. Now if I let in denote integral xn exponential x dx, it means that I can write here that in will be equal xn exponential x minus n minus 1, because this place is n minus 1. So since in denote this, now that I have x minus 1, I will write it like this. Now this is the reduction formula for integral xn exponential x. Now look at the example. If I want to integrate something like this, integral x raised to power 3 exponential x dx using reduction formula, I will just see that xn is equal in is equal xn exponential x minus n, then n minus 1. This is the reduction formula which we know. So what I will do is, this one is 3 and here is 3, so I will say I3 will be equal x raised to 3 exponential x minus 3, then n minus 1, here is 2. Then I will now come, I2 will be equal x raised to 2 exponential x minus 2, then I1 because of n minus 1. Then I'll now come again, I1 will be equal x exponential x minus 1, then I0. Then I0 will be x raised to 0 exponential x. Of course, this will be exponential x. So with that, we can integrate things that should be very long at a very short time. So that means I will see I3 times I2 times I1 times I0 will give me the whole of the integration. That is the same thing as x3 exponential x minus 3. Now I2. So I2 becomes x raised to power 2 exponential x minus 2 I1. Then I1 is x exponential x minus I0. Okay, so I0 is exponential x. Look at that. So I will now have x cubed exponential x minus 3. Then we have x squared exponential x minus 2, x exponential x minus x. Look at that. Then x cubed exponential x minus 3, x squared exponential x minus 2x exponential x plus 2 exponential x. Then x cubed exponential x minus 3 x squared exponential x plus 6x exponential x minus 6 exponential x. Then finally, you can write it like this, that integral of x cubed exponential x dx will be equal exponential x, then x cubed minus 3x squared plus 6x minus 6 plus c. So look at that. And if you use integration by parts, you can also get that. Then that also leads us to reduction formula for integral xn sine x. How do we derive that? Reduction formula for integral xn sine x. Now, integral xn sine x dx will be equal uv minus integral v du. And so we know that this one is u. Then u is xn. U will always be this. Then v is integral of sine. Of course, if you integrate sine, you have minus cos x. So minus integral v, that is minus cos x, then du. So if you differentiate this, you have nx raised to n minus 1 dx, and that will give us minus Sn cos x plus n, look at that, plus bring out n out, and then we'll have integral xn minus 1, then cos x dx. So we cannot stop here because this is cos. We need sine where we started. So we can go again and say minus xn cos x plus n. Yes, then we integrate this, which will give us u. U there is x n minus 1, x raised to n minus 1, that's u. Then v. V is the integration of cos. That will give us sine, that's uv, minus integral v. V is sine x, then du. Du is n minus 1, x raised to n minus 2 dx. Okay, so look at that. That is du. And this will give us minus x raised to n cos x plus n, then x raised to n minus 1 sine x minus, look at this, I'm going to bring this out. So we'll have minus n minus 1 integral of x n minus 2, then sine x dx. Sine x dx. So we see that here we now get things that resemble here, but we are going to replace this, the whole of this, by I n raised to minus 2. So we will have something like this. Let I n denote integral of xn, then sine x dx. Then we'll have that I n will be equal minus xn cos x plus, this will be n x n minus 1 sine x minus n minus 1, then we have I n minus 2. Okay, so if we multiply these two, we'll have that I n will be equal minus xn cos x plus n x n minus 1 sine x minus n minus 1, then I raised to n minus 2. So this one is the reduction formula for integral xn sine x dx. This is the reduction formula. So we'll do one reduction formula again for xn cos n. That is reduction formula for integral xn cos x dx. All right. From here, okay. So we know that integral xn cos x dx. By integration by parts, you have uv minus integral v du. By using integration by parts, you can use integration by parts to bring out this thing. That is where we started. So this will give us u. Now u here is Sn. V is when you integrate this, where you have sine x minus integral v sine x du. Du is n x n minus 1 dx. Alright, so Sn sine x minus, I can bring this n out, so we'll have integral xn minus 1 sine x dx. Alright, and what I have here is sine, y here is cos, so I have to go again once to have that Sn sine x minus n, right, minus n, then Sn minus 1, that is u v. V here will be minus cos x minus integral minus cos x, then du. Du here is x minus 1, n minus 1, x raised to n minus 2 dx, right? So, and then that would be Sn sine n minus sine s minus n, then minus Sn minus 1 cos x. Then here we have plus, because we are going to bring this, we have n minus 1, then integral of x n minus 2 cos x dx. So we see that in this place we are able to come back to where we started. So we can now let in equal integral of Sn cos x dx. And this will give us that in will be equal Sn sine x minus n minus x n minus 1 cos x plus n minus 1, then in minus 2. Look at that. And that means in will be equal n x raised to n, yes, sine x minus, of course this time this will give us plus n x n minus 1 cos x, then this time this will give us minus n minus 1, then we have n minus 2. So this one become the reduction formula for integral Sn cos x dx. There are so many reduction formulas depending on the function. So now we are looking at the definite integral. Let's take example. Evaluate x squared minus x plus 2 dx. Now see how this one is. It has this one called upper limits. This is lower limits. So it's just the same integration. But one thing about this is that you are not going to put c when you are integrating, because the upper and the lower limit will cancel the 2c. So what we'll do is the solution integral from 1 to minus 1 of x squared minus x plus 2 dx. First, you keep the upper and the lower limits and then integrate these parts. That is x squared minus x plus 2 dx, which is equal integral x squared dx minus integral x dx plus integral of 2 dx. Of course, this will be x cubed over 3 minus x squared over 2 plus 2x. Then we put 1 and minus 1 to have 1 cubed over 3 minus 1 square over 2 plus 2 times 1. Then minus, look at that, minus, you put the downside here, which is minus 1 cubed over 3 minus 1 square over 2 plus 2 minus 1. So here we will have 1 over 3 minus 1 over 2 plus 2 minus 1 over 3 minus 1 over 2 minus 2. So here, if we take the LCM here, we will have 6. So this is 2 minus 3 plus 12 minus, here is 6 again. Then we have minus 2 minus 3 minus 12. Now the whole of this place is 14 minus 3, which is 11 over 6 minus the whole of this gives us minus 17 over 6. That gives us 11 over 6 plus 17 over 6, which gives us 28 over 6. So the definite integral will always give a value, a real value. Okay, so